has maximum 111 in BCD. So for example, when I press some button, it will show, right, on the display, it will show this number, decimal number, but it will show only when I push. When it's pressed, when I release, you can see that it's come back to the 0. So actually, in order to, for example, I press 5 and I release, if I want that this screen still shows, for example, 5, I need some memory device here to add some memory device. And we can use flip-flops, and concrete we can use latch, and latch is some simple memory device that can hold, for example, in this case, 3-bit information, and it will be on the display. So let me show you the next circuit, this one. So you can see, actually it is similar to this one, but here I added some AND gates. You can see 8 input AND gates, and also I added 2 integrated circuit. You can see here 7475. So this, it's called latch. So in this lecture we'll study. Also, first let me stop this one and run this one. So for example, I will, what difference, when I start this program, it will show 7. Here you could see that it showed 0, right? So for example, I press 5 and I release, you can see 5 still here on the display. I can, for example, press 1 and I release, and you can see that it still show 1. So this latch, 2 latches, they perform some kind of, temporary memory that hold the information from the encoder and send to the display, to the output. Okay, here you can see in the binary, right, in BCD, but it is inverted. We need to invert to show it properly. Okay, so actually today we will study flip-flops, and we'll study this kind of devices. So let me come back to our lecture and we'll continue. Okay, so engineers in electronics, they classify logic circuits into 2 groups. So actually we learned first one, right? Logic circuits. First is combinational logic circuits. So it's based on just logic gates such as AND, OR, and NOT gates. But there is also, okay, something strange here happening. I don't know how to. Oh, fine. So here you can see the pronunciation, guys. So if you have opportunity, always check pronunciation. It's called, we need to pronounce it sequential, right? Sequential logic circuit. So what is a sequential logic circuit? So sequential circuits involve timing and memory devices. So the basic building block for the sequential logic circuits is the flip-flop. You can just name it just FI, double FI, flip-flops. So flip-flops are wired to form, for example, such devices as counters, and in the lab we already devised counters. Also we'll study shift registers and various memory devices. So flip-flops, it is fundamentals to construct this kind of devices. Counters, it will be the next theme. In the next lecture we'll study counters. Then we'll study shift registers, and we'll also study some memory devices. So flip-flops, it's very important. You need to understand what is and how it works, what kind of flip-flops we have in its operation modes. Okay, so first we'll consider the RC flip-flop. So here you can see the logic symbol for an RC flip-flop. So let's consider. So you can see that on the right side it's inputs, and on the left side inputs, on the right side outputs. So you can see that it has two inputs, right? So first set and second reset. So just in short, S and R. Also you can see here the bubble. Bubble means it's active low. It means to activate this logic symbol, you need to apply 0, not 1. Okay, so in the output you can see it has two output, Q and not Q. So for example, if Q will be 1, not Q will be 0. If Q will be 0, not Q will be 1. So it's just normal and complementary. So it's just they're always opposite to each other. Okay, so you need to know that in the RS flip-flop has two inputs. I mentioned S and R. So S is set and R is set. Okay, so and Q and not Q. So in flip-flops, the outputs are always opposite or complementary. I mentioned already this one. It's also clear from this diagram. So what means S and R? And also I mentioned that the inputs are active low. You need to know that when we see in the input this bubble, it means that we activate by low, by 0. And the RC flop may also be referred to as an RC latch. So sometimes we can say flip-flop as a latch, but not always. So when we use it as a memory device, we can see it as a latch. So term latch refers to its use as a temporary memory device. A latch such as RC flop in this figure can hold 1 bit of information. So this one can hold only 1 bit information. If you need to hold 2-bit information, you need this kind of devices. If you want to 4, you need to 4. So next, now you should know that if you have some logic device, some logic symbol, so we can describe it by the truth table, right? So let's consider truth table for this RC flip-flop. So here is the truth table. So let's consider carefully. So here you can see on the first column. Guy, is it okay? Can you hear me?
Yes, we can hear you.
Okay. So first column is mode of operation. So actually it has 3 operation modes that we can use. It's set, reset, and hold. Also, there is some other operation mode prohibited, right? But do not use in the prohibited mode. So next 2 columns, it's inputs, S, set and reset, and outputs Q and Q, not Q. So what kind of effect on output it will have this combination? So let's consider, okay, let's start from the prohibited. When you apply to the inputs and to the set and reset 0, so you activated both S and R. So output will be 1, 1. So it is a prohibited, forbidden. You do not need to use in this state. Okay, next set. So set, when you activate, when you apply to the pin S, when you apply 0 and to the reset 1, you can see that outputs, this normal output will be 1 and not Q will be 0. So actually we can say that we're setting Q to 1. So we send to the normal output, we send 1. So what is the reset? In the reset, you need to apply to the set 1 and activate reset. So you apply 0 to the reset, and in this case, you kind of clear normal output. So it will be 0, and of course complementary is always opposite, it will be 1. But also it has hold mode. What is a hold mode? When I apply to the S and R 1, 1, it means that what was before will stay. For example, if before was, for example, 0, 1, and you applied 0, 1. Then you apply to the set, you apply 1. This output will be still 1, 0. So it will hold the previous outputs. For example, if it was this reset mode, for example, it was S1 and reset was 0, it means that output will be 1 and 0 and 1. Then you apply to the hold 1, and it will normal in complement will not change and will be still 0 and 1. So we call this hold mode. Okay, so actually I set all of these notifications. Do not need to. So you need to understand. So what is a prohibited state? Because you do not need to use the flip-flop in the prohibited state. So you need to understand what is set condition, reset condition, and hold condition. Okay, so, but actually there is a ready integrated circuit that contains, of course, not one, several this kind of RS flip-flop inside one package, right? But actually we can assemble the RC flip-flop from the NAND gate. So for example, you can see how can you get the RC flip-flop by using the NAND gate. So it is a NAND gates. So what's interesting here, so one input of the NAND gate, for example, is above here, it will be S, and one input of the second NAND gate will be R. What does it mean, this overbar? It means that you activate by law, that's it. But other inputs of the first NAND gate, you should connect to the outputs of the second NAND gates, and the second input of the second NAND gate, you need to connect to the outputs of the first NAND gates. So, of course, the truth table for this assembled circuit will be the same as in the previous one. So, guys, let's consider this in Multislim. So I will open, I guess this one should be. Tomorrow on the lab, you will do this kind of work. So let's check. So let's come back to what is the prohibited S and R 00. So before we start, guys, always make sure that it is not in prohibited state. Now it is in prohibited state or not?
I think no.
So let's me.
But if you consider the opposite, like when
this will be prohibited state, right?
Yes.
Yes. So when we start, make sure, even in the simulation, try to do it. So let's start. So what do you think? What kind of mode is this? It is a hold mode, right? Oh gosh, what's going on? Okay, so let's start. When set will be activated, it means that I should apply to it 0. So you can see that 1 and 0, right? It is according to the truth table. When set 0 and reset 1, output will be 1 and 0. So I think you can see why it's moving. I could not understand. So, okay, so next you need to go to the hold mode. Then you can see that it doesn't change because it's on hold mode. When I press R, I will activate R. So you can see it will clear the normal output, it will become 0 and 1, and this complementary output will be 1. So if I will come back to the hold mode, you can see it will stay in this hold mode. So you can see it is a kind of sign of memory, because it will remember in the hold mode, it will remember the previous state and will hold this previous state in the hold mode. So actually we can use this in the example that I showed at the beginning for the push button. Okay, so let's try again. So now I will activate the set. You can see it will 1, 0. So I think it's very simple. It's not too hard to understand. Okay, let's continue. So what else? Of course, except the truth table. When we'll do with the sequential circuits, we often will use waveforms. So waveforms is kind of diagrams that is very useful. So let me show it. It's similar to the truth table, but it's more, it's similar what you see in the oscilloscope. Actually you can see your real signal. So it is a diagram for the RC flip-flop. So you can see, for example, here, this diagram shows the voltage level and timing between inputs and outputs. So you can see that the horizontal distance, this horizontal distance, it's time, and vertical distance is voltage. Okay, so let's consider it careful. So you can see, for example, so set, you can see here set it's 0, and R it's 1. So it is in the set mode, right? It means that Q will be 1 and not Q will be 0. Then second, let's consider reset mode. In the reset mode, set will be 1, reset will be 0, and you can see that normal output will be 0 and complementary output will be 1. So again, set, it's similar to this one. And hold. So in the hold mode, the output will be the same as in previous. So previous was set, and in the hold mode, the output will be the same as it was on the set mode. So this kind of waveform diagram you can use instead of the truth table, but this actually shows the same thing. Sometimes it's very easy to interpret, to understand the principle of working some devices by using waveform diagram, because it shows you timing. In the truth table you could not see time. You can see just some voltage level, that's it, but here you can see time. Okay, so let's continue again the RC flip-flop. So actually in the first lecture, maybe in the second lecture, we studied, just we mentioned that there is 3 types of multi-vibrators, right? So what kind of, can you recall?
Astable, bistable, monostable.
Yes, the monostable, the stable, and bistable multi-vibrator. So actually the RC flip-flop is one of several bistable multi-vibrators. And the RC flip-flop is most commonly known as a latch. So sometimes we say to the flip-flop as a latch, but latch has some precise definition, and we'll talk about in this lecture later. Latch is a fundamental binary memory device for holding data, and actually you see that RC flip in the hold mode can actually hold the data, yes, from the previous mode. Latches are commonly used as the output of digital devices to hold the data until the next device is ready to receive the input. So, and of course, latches are commonly organized into groups. So in the lab, we will use 4 bits, 8 bits, and more into the register. So register we will study also in some of the future lecture. Okay, for example, 8-bit register can hold byte information. You should know that byte, yes, it's 8-bit, right? Bits. Okay, but also you should remember that RC flip-flops, we actually used it for the switch debouncing. So when we use the flip-flops for the switch debouncing, we could not say, but we could say it's latch, but the latch, its purpose actually to hold the information. But flip-flops can be used for other purposes, not to hold the information. For example, for the switch debouncing. Okay, so next type of RC flip-flop, it's called clocked RC flip-flop. So let's first consider the logic symbol for the clocked RC flip-flop. Actually, you can see that it's the same to the previous one. Can you see the difference? And can you see me the difference between the just RC flip-flop? What difference?
The clock.
Yes, it has additional input, right? That KLK, it means clock. But what also is the difference in this type of clocked RC flip-flop? What other kind of difference can you see? So if you recall, in the set here we have bubbles, right? In the reset also we have bubbles, right?
Yes.
Guys. So here you could there is no bubbles. It means that you activate by the high, not low. So it's also the difference. So it's almost the same, but has an extra input label KLK. Okay. So let's consider the waveform for the clocked RC flip-flops, and let's consider in more detail how it works. Actually, I did not put it right. Let's come back. For example, you apply here, for example, to the set, you apply 1, to the reset 0. But your normal output will, the output will be set by the clock signal. So it's not enough, just apply to the set, to the reset some kind of voltage, but also you need to apply clock signal, and clock signal actually will generate trigger. We say trigger the normal, the output normal, of course the complementary output. So let's consider this waveform diagram in more detail. So let's consider the first, you can see that S, on the S it's 0, right? And also you can see that reset is also 0. Okay, so here you can see that we apply pulse, one pulse to the KLK. So let's consider to the output. So when S is, it's low, right? Yes, it's low. R is also low. Yes, you can see that Q is also low, and not Q, high. Okay, so when we apply one impulse during this stage, you can see that it does not affect the Q or not Q. So let's consider the moment when set becomes high, and you can see that R resets still the 0. So actually we activated S. But if you will look at the output, you can see that output will not change to the high. It will change only when we apply one pulse, when we apply signal to the clock. You can see that in this rising edge, when the clock signal will rise, you can see that output will go to the low. Normal output will go from the 0 to 1, and complementary or not output will go from the high to 0. Okay, so you can see that we hold for a while the set in the high position and reset in the low position, and you can see that we have some impulse, right? 3, but it doesn't affect the outputs. Okay, so here guys, you can see that S goes 0 and reset still low. You can see that we have other impulse, but it doesn't affect the outputs. So it is in hold mode, we say. Then you can see that R goes high and set is low still. So we call this preset mode because it will wait until the clock input will get the signal. And you can see that 5 impulse gives that signal, and during this rising edge, you can see that output will trigger, right? It will change from the high to the low, and you can see that NOT will go from the low to the high. Then our reset is still high and set is still low. You can see it doesn't affect, this impulse 6 doesn't affect the outputs. Then it's again goes to the hold mode, and this 7 impulse also doesn't affect the outputs. So maybe it seems a little bit confusing, but if you will think about it and you will do the lab works, I think it will be clear. So I think, okay, what you should know here, you should know that there is some preset position. So it is a preset position. For example, when we change set from 0 to high, it is a preset condition. Why? Because next it will wait the signal from the clock. Then clock will permits that will change the Q. Next, the output of the clock RC flip-flop change only on clock pulse. Yes, you can see that it will change, output will change only on the clock pulse, right? We say that the flip-flop operates synchronously, guys. So it operates in step with the clock. So you need to also understand what means synchronously. So when we have this clock signal, then output will react, will be triggered. So we say it operates synchronously with the clock. Okay, next, synchronous operation is very important in most digital circuits where each step must happen in exact order. So this type of operation is very important in digital system. So what kind of other characteristics? Another characteristics of the clocked RC flip is that once it's set or reset, it stays that way even if you change some input. So yes, guys, you can hear, we already, for example, here, we already activated the set. You can see that clock input, we have some signals here, 3, for example, 2, this part, 3, and it doesn't affect the output, right? Similar with the 4, 7, it's 1, I forget about, it's other types. This memory characteristic, which is extremely valuable in many digital circuits. The characteristics is evident during the hold mode of operations. So you can see that 1, also 4 and 7, it's hold mode operation. Okay, so it was the waveform diagram. So next, I think we need to consider the truth table. So it was the waveform diagram. Here you can see the truth table for the previous clock RC flip-flop. So actually, it shows the same thing as a waveform there. So hold mode, you can see hold mode. When we apply 0, 0 to S and R inputs, so outputs will not change, it will stays the same as it was before, so no change. In the, of course, reset mode, so in the reset mode, you should apply to the R 1 and set should be 0. Then you activate by the clock impulse and it will change, right? So if your output was 1 and 0, it will be 0 and 1. So it is a set mode. It's opposite to the reset. And also there is some prohibited mode, so you do not need to use in the prohibited mode. So actual prohibited mode, when we activate both S and R, when we apply to the S and R 1, 1, output will be 1, 1, and you do not need to use in this mode. So I already mentioned that this type of RC flip-flop is active high inputs. because we don't have any bubbles, and you can see that by applying 1 to the set, normal outputs will be 1. So also we can wire clocked RC flip-flop using NAND gates. So here you can see that we add to the usual RC flop, we add 2 NAND gates, right? You can see that we added 2 and there's 2 NAND gates, and you can see that 2 inputs are connected, wired together, and we call this clock. And other inputs will be S and R. So tomorrow on lab work, we will try to assemble this circuit and study its property. The Kelka input may be labeled with CDS. Sometimes you will see that this can be labeled as C or E. Enable. So C it means, I think it means clock. E it means enable. It means activate. Okay, so it's important to remember that the memory characteristics exhibited by flip-flops are among the fundamental reasons why digital technology has become so widely used in modern electronic products. Because there is also the analog electronics, right? But in the analog electronics, it's very difficult to construct simple memory device. But by this digital electronics, you can easily just use these flip-flops. You can hold, for example, 1 bit of information. So let me show this on the multi-slim. Can you see my multi-slim?
Yes.
Yes.
Okay, so guys, I've tried to test this one, but for some reason it has some bugs, some errors. I could not figure out why, but it works. But not works. I should it work, in a real hardware version. But anyway, it works. Let's just, for now, let me remove this wire and let's start. So I think it's too high. Let's change the to 5. Okay, it is this circuit, right? So it has S3 input, S set, clock, and reset in 2 outputs. So you can see. So this it's S set. In the middle, this it's clock, and here it is a reset. So let's come back to the truth table. So what is a prohibited state? 1, 1. So make sure that it is not in the prohibited state. So it is not, right? So let's apply. So let's give the, let's activate set. So we activate set by applying 1. So you can see normal output will be 1 and not output will be 0. So it's fine. Okay, so next I will go to the hold mode. You can see the output is still 1 and 0. But now, guys, maybe it's too fast, but I want that you see the, okay, let me change the frequency. To the 1. Okay, so now it's on hold mode 1, 0. When I press when I activate the reset mode, what will be the output?
0, 1.
Here will be 0, 1, but it will not be changed immediately. It will change according to the signal. So I will look now. You can see it's lightning, so it has 0. It's activated. So you can see it's not changing. Wait. Can you see when here clock when clock signal from the clock goes from the 0 to 1, it will change. Now let me go to the hold mode. You can see in the hold mode it will hold. It will remember the previous mode. It will be 0, 1. And now let's wait. So you can see it will change according to the clock signal, right? So, but when I will try to, for example, when I go to the prohibited state, you can see some error occurs. Can you see some? My digital clock doesn't work anymore. I don't know why, and you can see there's some kind of error. So maybe it simulates this error. I don't know, really. Could not explain this behavior. So let's next show me the connection with the oscilloscope. Okay. So it's too low just. So now let's wait. But for some reason my I don't know, it doesn't work. I don't know why, but before I've checked, it worked, but now it doesn't work. So let's check like this. There is some bug from the program and I could not explain this. Okay. So I will show with other type of device, but not now. Let's continue with our lesson. Maybe on the lab work and I will show you this. Okay, the flip-flop we can start on the next. So now, please do not forget, guys, we have 5 minutes to record our attendance. So please now go and record your attendance, okay? Then I will now find the other flip-flops and we'll show you on the oscilloscope. So for now, while I'm searching for the flip-flop, guys, you record your attendance. It is this one. So this, it's also flip-flops. Yes, but it has some additional set and reset. It is also S, but it has additional set and reset. In the later I will explain, but for now I will just want to show you the. So I will copy this part. So what else I need? I think I need clock. I need clock. And I will connect. So for a while, forget about set and reset. It's just additional, you know, inputs. And you can see that they don't have any bubble. It means that we should connect it to the VCC. It also should be connected to the VCC. No. We should not to activate this one. It should be connected to the ground. Ground. So for a while, do not think about this part, why I'm connecting to the ground. So just consider this part and let's consider our outputs. So can you see? Is it okay? Guys? Are you here?
Yes, we can see.
Okay, so let's add oscilloscope and check this clocked. It is clocked RC flop. First, let's make sure that it's worked properly. So now it's in prohibited state, right? It should not be in the prohibited state. Okay, so let me rerun this one. So actually, okay, let's wait this clock signal. You can see it's working, right? Now it's hold mode. Let's wait the clock signal. So fine, but I want to show you on the oscilloscope because it's more, you know, understandable when you see from the oscilloscope. So let's come back to the hold mode. So let's wait for a while. So here below, it is the oscilloscope. Above, it's okay, let me change this one. And wait. So can you see this?
Yes.
Yes.
Okay, so next come back to the hold mode. Now it will not be changed because it will change on the rising edge from the low to high. So let's wait. So now our oscilloscope should go down. So you can see that oscilloscope go down. Then when this purple light, it should go down. Our output should go down. So let's wait.
Yeah, maybe you increase frequency. It's too.
Yes, but for some reason the timing is changed. Before it was work faster. Okay, let's wait. So can you see? Okay, fine. So you can take break and we'll continue. Guys, but before you will take break, if you record your attendance, let's finish this meeting and leave this meeting and reconnect to the next meeting, okay?
Okay.
So see you in the next meeting, okay?